Okay, so according to my plan, we will try examples now. So, so I will start with sum of independent random variables, not necessarily identically distributed. Well, we'll start with this example, but then we'll just look at sum of independent random variables not identically distributed, and then remove the independency hypothesis. So the first set of examples, these are sum of independent random variables. Okay, so there's a subcase, easy case. When you really take a sum of IIDs, so well, Sn will be a sum from 1 to n of variables Ti, which are sampled of variance 1 and I will need the third moment also. So I assume that my Ti, they have convergent moment generating functions as this morning. And also, so the Ti's, they are IID. Distributed and independent. Okay, and I look at Xn, which is Sn divided by n to the 1/3. So usually one looks at Sn divided by n to the 1/2, but for mod Gaussian convergence, we just scale by n to the 1/3. And so let us compute the Laplace transform of this Xn. So if I try to compute that, then it is equal to the nth power of exponential z Ti divided by n to the 1/3. Okay, and I can do a Taylor expansion. Plus. Okay, so this terms comes from the fact that the Ti square has expectation equal to 1, so this is why you have a 1 here. And then if you look at the third term, is L over 6 Z3 over sorry, there's a mistake. N. Okay, plus a small o of 1 over n, which is locally uniform in Z. Okay, and the whole of this to the power n, and so I can write it if I want as like that. Okay, so what happens when I take the power n of this quantity? Well, here you will have n divided by n to the 2/3, so we will have a Gaussian, but of variance n to the 1/3. Sorry, there is no minus here. It's a plus. Okay, and when I take the nth power of this, so you have 1 plus something divided by n to the power n, it is equivalent to exponential of LZ3 divided by 6. Okay, and this one, okay, sorry. It's 1 plus small of 1. Okay, so what we have proven is that we have mod Gaussian convergence with parameter Tn equal to n to the 1/3, and this limiting function psi of z. Xn. With parameters Tn, this is n to the 1/3, and limit psi of z, this is equal to exponential LZ3/6. Okay, so if I apply my large deviation result, what I get is that the probability that Sn is bigger than n 2/3 times x for x positive. So this is the same as the probability that Xn is bigger than this. And here we really have Tn times x. So we know that this will be equal asymptotically to this quantity. And then psi of x, so exponential okay, so you have a Gaussian tail, but multiplied by something that is non-trivial. And what is interesting is that so if you do it on the other side with x negative, right, so if you look at probability that Sn is smaller than minus n to the 2/3 x. So what you get is the same formula, but there will be a minus x at some point. Okay, so what this means is that, so if you look at the central limit theorem, Sn over n to the 1/2, it is distributed like a Gaussian. So a Gaussian, it is symmetric. You have tails that look the same on the right side and on the left side. But if you look at the order n to the 2/3, and so suppose say that L is positive, this quantity will be much larger than this one. So you have a breaking of symmetry just at this scale n to the 2/3, and not before. Before everything was symmetric. But at this scale n to the 2/3 for the fluctuations, you have this breaking of symmetry. Okay, so this was well, the easiest example that you can look at, but already it's something interesting that you have this asymmetry at this scale n to the 2/3. Okay, so now I will look at another.
Is the sign right on that? They look like this.
So there is a minus.
Minus x and minus x cubed.
Yes, but so this one is if you take
same.
x, okay, x is again positive.
Oh, x is positive. Okay. Yeah.
Okay, and you look at the tails, so like you have a Gaussian, but okay, so for instance, if L is positive, here the tail will be a bit smaller than on the other side at scale n to the 2/3.
1 plus the little 1.
Oh yeah, of course. Okay, so this was the easiest example. So now let's look at another sum of independent random variables, but this time not identically distributive. So in order to be able to make computation, we just look at some of Bernoulli random variables. So I take Sn equal to a sum of n Bernoulli random variables that are independent of parameter pi. So the b I are independent, and pi is a parameter of bi. So Okay, and I assume that the sum of the parameters pi go to plus infinity, so my sum, it will go almost surely to plus infinity, but if I scale it, I can expect to have a limiting result, so I suppose sum of the pi go to plus infinity. And so in order to have a mod Poisson convergence, in fact, we need that sum of pi squared is finite. Okay, and in a moment I will take pi equal to 1 over I, which is an interesting example that satisfies these two hypotheses. Okay, so if you have...
So the probability is just bigger than pi? What is pi?
So pi is just a parameter of my ith Bernoulli parameter, Bernoulli variable. Okay, each...
No, it's because I think it's rewrite the equality. No.
That I understand. Okay.
Okay, yeah, sorry. So let us compute the asymptotics of the Fourier transform of Sn. So the Fourier transform of Sn. So again, I have, well, sorry, not the Laplace transform of Sn. So again, I have a sum of independent variables, so it will be equal to a product. So it's equal to the product of the expectation of exponential z bi. Okay, and this is easy to compute because you only have two possible values for bi. So what you obtain is the product over I of, so either exponential z with probability pi plus 1 minus pi.
So can the pi's be 0?
Yes.
So you could have that
yeah, but it's just
the first 10 are 1 and then all the rest are 0?
No, because so you ask that.
Oh no, you have to go to infinity.
Yes, we go to infinity. But I mean to put pi equal to 0, it just means that you forget this variable. It doesn't exactly. Yeah. It doesn't count in the set.
Okay.
Okay, so this one.
So these are going.
So it's
in the whole. They're going off to 0, but not too fast.
Yes, exactly, because so this
that means they're going
pi
to 0.
goes to 0. Yes.
Going to 0 uniform.
Okay, so so this thing you can write it in another way. So okay, so if you assume that pi goes to 0, this is almost, so 1 plus something that goes to 0, it's almost the same as exponential this thing. So what I'm going to do is multiply on both sides by this. Okay, so on the one hand, this quantity here, this is exponential sum of the pi's from 1 to n times exponential z minus 1. And this is the Lévy exponent of a Poisson law. So here you have the Laplace transform of a Poisson law of large parameters. So maybe let us give a name. Let's call this, I don't know, well, Tn actually. This is equal to Tn. And this one, this thing, this product here, in fact, it is a convergent if you take the product up to infinity. It is convergent because if you make, okay, so if you do a Taylor expansion of this, what you will get is something, so, yeah. So we'll get something like that. And this is a convergent infinite product because the sum of the pi square is finite. So, in fact, what you obtain is, so up to 1 plus model of 1, you obtain the infinite product, and so I've just shown you that it was convergent. And then something that is, so this will be your psi of z. And then you just have the Laplace transform of Poisson law of parameter Tn. Okay, so you have mod Poisson convergence. With parameter Tn. So Tn is the sum of the pi's up to order n, up to index n. Okay, so there is an interesting example is when pi is equal to 1 over I. I believe there is a motivation for this. So the example is the following. So you look at a random permutation. So let sigma n be a random uniform permutation of size n. So this means that it has probability 1 over n factorial because there are n factorial different permutations. So uniform probability. For every sigma in Sn. Okay, and so when you have a permutation, you can decompose it in cycle, and you can look at the number of cycles of your permutation sigma n. So I set xn. This is a number of cycles of sigma n. Okay, and I want to study the asymptotics of xn. So there is a way to write xn in law as a sum of independent Bernoulli variables with parameter pi equal to 1 over I. So I claim, and I will just show you in a moment why this is true, that this is equal, so in law, to a sum of Bernoullis of parameter 1 over I, so independent Bernoullis, of parameter 1 over I with I going to 1 to n. So why is this true? Well, there is a way to actually to construct all the sigma n's, so sigma 1, sigma 2, and so on, up to sigma n, in a coherent way, and such that at each time you add a cycle with probability 1 over I. Well, 1 over n when you go to sigma n minus 1 to sigma n. So more precisely, so for every permutation of size n has a unique writing, so write uniquely as a product of transpositions, so as sigma, so it's the following. With ik each time that is smaller than k. So for each index ik, you have k possibilities. So what I say is that
you read it from right to left or left to right?
Yeah, that's a good question.
I think it's from.
Yeah, it might be in the
Right.
other sense, but
Yeah.
it depends how you compose your permutations. Yeah, it's not very important. So to create a permutation of size n, so what you do is that first you make a permutation of 1 with something smaller than 1. Well, then you don't have any possibility. Then, once this is done, you make a permutation of 2 with an index I2 smaller than 2. Then you do the same with 3 and so on. And this is a unique way to decompose sigma n as a product. So this can be equal to the identity if I n is equal to n, for instance. But otherwise, it's a transposition. It's a unique way to write Sn as a product of n minus 1 or a smaller number of transpositions. And with this writing, what happens is that, so each time, so you can consider, for instance, if you stop here at index n minus 1, what you will obtain is sigma n minus 1. And to go from sigma n minus 1 to sigma n, so you just multiply by the transposition here. And what is true, what happens is that if in is strictly smaller than n, then you don't create a new cycle because you just add n in a cycle of sigma n minus 1. And otherwise, if in is equal to n, then you add a new cycle. Well, you add just a fixed point, which is a new cycle in your permutation. So the number of cycles, it is easy to see on this decomposition. So xn is the sum from 1 to n of the indicatrix that, so maybe I should put a j, of ij equal to j. And here's so all of these random variables are independent, and each one is a Bernoulli random variable with parameter 1 over j. Okay, and it happens that what I've just done here holds for this sequence, for this sum of Bernoulli random variable, because indeed, if you take the sum of 1 over I, if I go into from 1 to n, what you obtain is a harmonic number hn, which is essentially of size log n, so this goes to plus infinity, and sum of 1 over I squared, this is a zeta function, and this is pi squared over 6, so this is finite. So this result holds. So I know that xn converges in the mode Poisson sense. So xn converge mode Poisson with parameter Tn, so which is equal to the nth harmonic number, that is to say the sum from 1 to n of 1 over I, and with limit. So what is written over there, but with pi equal to 1 over I, so psi of z, this is okay, but so this infinite product, it happens to be related to the gamma function evaluated at exponential z minus 1. So if I'm not mistaken, it's 1 over gamma of exponential z times exponential of gamma exponential z minus 1. Is it true? Yes, that's it. Okay. So in fact, it can be written in terms of the gamma function. Okay, and so if you use asymptotics of hn, so hn is equal to log. Okay, so here's this constant gamma. This is Euler's constant. And this Euler constant, it also appears in the asymptotics of hn. Hn is equal to log n plus gamma plus a small o of 1. So by combining these two things, you can write an asymptotics for the probability that xn is larger than 1 plus epsilon times log n. Okay, and what you obtain is the following. So you obtain exponential minus log n times the Legendre-Femshell transform of the Lévy exponent of a Poisson law, and this is given by this formula. And this quantity is positive. So then you have to divide by square root of 2 pi log n. Okay, so then, so there is this, so we are in the lattice case, so there is this 1 over 1 minus exponential minus h that appears, and h here is log of 1 plus epsilon. So this term in tree gives you something like that, in fact. Okay, and then there is this gamma function that appears. And I guess it's gamma of square root of 1 plus epsilon. So it comes from, so here you have the second derivative of this quantity. Well, or not this quantity, of eta. And so, yeah, that's why, and okay, so here, sorry, it's 1 plus epsilon. Okay, and again, 1 plus a small rho of 1. So you get some precise asymptotics of, so this time of really of large deviations, because this is a regime of large deviations, for instance, the number of cycles of a random permutation. And so what I've just, so here there is a simplification because you have this infinite product that happens to be equal to the gamma function, but in general, we have just the infinite product with the phi I, which we know to be convergent, and we can write everything in terms of it.
Oh, so, do you know whether the infinite product in the case above is the characteristic function of a random variable?
It's not in general.
I know it's not in general, is it? I wonder if it is in this case.
So there is a simple criterion to know. So here it seems to work, but there's a simple criterion. So first of all, you need the psi of this should go to 0 when psi goes to plus infinity or minus infinity. Okay, by Riemann-Lebesgue lemma. So for instance, if you're in the previous cases, psi was an exponential of x to the third, and this doesn't go to 0. So this is not the Fourier transform of anything. So I don't know with the gamma function. So you have to look at the gamma function on yeah, I don't know. I'm not sure. I have to look at the gamma function and to see if really it corresponds to something. I don't think so. Usually, so the thing is that, I think you have asked me this question already this morning. It's not possible to extract a random variable that would be the...
In general.
Yeah, that would be the information behind the noise. You can only extract something in the Laplace sense.
You know the two distributions, but you don't know. You may not be able to...
Yeah, you cannot subtract... and that's the thing. When you have a large noise, you cannot just subtract the noise. You have to do something clever in order to obtain information.
If it's a convolution, you know.
Yeah.
On this example that's on the top there, this is vague, but this seems like it may have the flavor of some kinds of applications in finance, because if you think of the different values of I, it could be different players. Usually there's some big players, but there are a limited number of them. And then beyond that, it's doing this. The other thing I'm wondering about is if you index this by Tn, by time, and fill in somehow in between, it seems like after after some finite time period, then it's very close to a Poisson process. The additional change.
Yep, but not for the tails. The tails, you have an additional
And
factor.
but that's, yeah, but I'm wondering if you have, so it's approximately a Poisson process, but you have a finer level of approximation. Is there another process that you could write down? That's one reason why I wanna know if this is.
You mean
already
better
correct.
than a Poisson? That's what you mean?
Can we say that it looks like a Poisson plus this kind of noise, or Poisson
Yeah, so-
adjusted this kind of way, to have something which is a
So we have
a stronger sense of
yeah.
convergence?
We have so it's a question of approximation by discrete laws that would be Poisson plus something. So we have another ongoing project on this topic. You can replace a Poisson law by a better approximation. So not really in this sense, in the sense of computing the tails, but for instance for Kolmogorov for total variation distance, say, for discrete random variables. And so there is a way, yes, to have a better approximation, so to replace Poisson law by something, a bit better. But yeah, for the tails, it's not really possible to do so, and I don't think the residue. Okay, so I don't know for the gamma function, but in many situations, the residue doesn't correspond to any law, so there is no hope to do so.
Well, let's, I guess maybe you can look at the whole thing. That's the research.
Okay, so so these were examples with some of independent random variables, but I also want to do dependent random variables. And to do so, I will need to introduce something called the cumulant and the joint cumulants of random variables. So this is like the second part of the examples. And so it will lead me to the method of cumulant, which is really a strong method in order to prove mod Gaussian convergence, in fact. Okay, so we'll start by recalling what is a cumulant, and also by telling you what is a cumulant, a joint cumulant of a family of random variables. So if I take a random variable with a convergent moment-generating function, so convergent, I mean in a strip around 0. Okay, so this generating function, when z is equal to 0, this is equal to 1. And therefore, when z stays small, you can look at the logarithm of this, the complex logarithm of this quantity. It is well defined. It is again holomorphic in the neighborhood of 0. So logarithm of this. This is a series that vanishes at 0. So it's Taylor expansion, right? It's like sum, so you start at n equal 1, of some coefficients, so that, okay, I will use the index R. Okay, and in this expansion, the kappa R of x, they are called the cumulants of my random variables. So kappa R is a cumulant of order R of x. Okay, and these cumulants, they can be written in terms of the moment of x. So for instance, if you look at the first cumulant, what you obtain is the following. So the first cumulant is just the expectation of x. And then the second cumulant is the variance. And then you can continue. So for instance, the third cumulant, this is given by this formula. And each time you have some kind of polynomial in the moments that gives you the cumulant of order R. Okay, so this is for one random variable, but so you can see them as, well, as other invariants on the moments, but that play some kind of similar role. And so for moments, you have this notion of joint moments, and similarly, you can develop a notion of joint cumulants of a family of random variables. So now if x1 up to xn is a family of random variables, like ça. Okay. Then I can define their cumulant. So by two ways actually that are equivalent. So by definition, kappa of x1 up to xr. So one definition is the following. So you take the derivative with respect to t1, tr of the logarithm of a joint generating function. And you take its derivative at 0. Okay, so you derive r times, and you take the derivative at t1 equal t2, etc. equal tr equal 0. Okay, so this is the first definition. And with another definition, so it can be written in terms of the joint moments of these random variables. So the formula is the following. So it's a sum. Okay. I will write the formula and then explain every term. Okay, so you take the sum of a set. So this set is the set of set partitions of size R. Set of set partitions. So of the interval 1R. So a set partition is a way to write this as a union, a disjoint union of parts. So something like pi 1, disjoint union pi 2, etc. Disjoint union pi index L. And then you take the product over these parts of the expectation of the product for each part of the random variables that with indices that fall in the part. So it's easier to understand, okay, and there is this mu of pi, which is -1 to the L minus 1, L minus 1 factorial, where L is the number of parts of pi. So it's easier to understand on an example with R equal to 3. So if R equal to 3, you have 5 ways of 5 set partitions of size 3. So you have the partition with 1 part, 1 to 3, then 3 partitions with 2 parts. And 1 partition with 3 parts. Okay, and to each of these set partitions will correspond a term in the sum. So to this one, so you have just 1 part, this is equal to 1, and then you take the expectation of the product of everyone, so this will give you with, say, x, z, and x, y, and z instead of x1, x2, and x3. So this term, if you have, for this one, so you have 2 parts, so this quantity is equal to -1, and this gives you minus okay, and for this one, so the coefficient is 2 factorial, so 2, and then just the product of the expectations. Okay, so the cumulant of 3 random variables x, y, and z, it is divided by the sum of these 5 quantities. Okay, so this notion is a generalization of the previous notion of cumulant of 1 random variable, because if I keep the same notations, then you can check that kappa r of x, it is a joint cumulant of kappa of x that appears r times. Okay, so on this side you have a joint cumulant, and here you have the usual notion of cumulants, and the two notions correspond. Okay, so why is it interesting to introduce this notion of joint cumulants? So it's interesting because if x is a sum of random variables, then the joint cumulant, well, it's clear that it is multilinear, and therefore you can expect to, well, you can try at least to decompose your cumulant kappa r by multilinearity. So joint cumulants are multilinear. It's also easy to see that they are invariant by permutation of the random variables. So in particular, this multilinearity, if you have something x that is a sum from 1 to n of variable ti, then kappa, the cumulant of order r of x, it will be equal to a sum of joint cumulants. So it takes the sum of our indices, I1, etc., up to IR, of kappa of ti1, ti2, etc., tir. And this joint cumulant, so there is something that is easy to see on this definition. This is equal to 0 if you can split your family into 2 independent families of random variables. So in this sum, in fact, some terms might be 0 if you have some kind of independence. Okay, so now how to relate this concept of cumulants and joint cumulants to mode Gaussian convergence. So in fact, so the following happens. So since this is multilinear, so suppose that you have a sum like that. Since this is multilinear, here you have the number of terms that you are summing. This is n to the r, right? So you might expect that if you look at each cumulant, so if you look, for instance, at the cumulant of order 3, it will be of order n to the 3, and the cumulant of order 4 will be of order n to the 4, and so on. But in fact, in many situations, the cumulant of order r, it is not at all of order n to the r, but of order, so sometimes it can even be of order n, in fact. You just have n terms and not at all n to the r, and this for every r. So in many situations, kappa r of x is not a grand tour of n to the r. Well, I mean, it's not of order n to the r. It is a grand tour of n to the, well, it can be something like big O of n, for instance. Yeah, it can be a big O of n, or n to the alpha with alpha strictly smaller than r. Okay? And this is important because it leads to Mod-Gaussian convergence. So I have a small computation to do. So I will make assumptions on my sum of random variable of this kind, and then tells you that it leads to Mod-Gaussian convergence. So I consider the following setting. So I take a sum of random variables. So I do not assume anything on the TIs. And here, capital N, it is something. So it can be, for instance, n to the square or n or something like that. Okay, and I assume the following. So assume that there exists two sequences. So alpha n going to plus infinity and beta n. So I do not assume anything on beta n, just positive, such that so the following is true. So you suppose that kappa index r of Sn is equal to alpha n times beta n. Okay, so it's the big O of alpha n times beta n to the r. Okay, which means that if I divide by beta n to the r, kappa r of Sn, it's a big O, so the constants in the big O depend on n, on r, and it will be important in the following. So it's a big O of alpha n. Okay, so you don't have cumulants that go with r in order. They all go to infinity, but at the same speed. Okay, so if you suppose that, then in many situations you have Mod-Gaussian convergence, so you just have to be careful about the constant here in the big O, and about you also have to control the first cumulants. Okay, so suppose more precisely the following. Okay, so I suppose first that the first cumulant is equal to 0. Okay, so this is I just subtract the mean. This won't change the other cumulants, so I can always assume that the first cumulant, which is the expectation, is equal to 0 and work with centered random variables. Okay, so then I will look at kappa 2. So this is supposed to be of order alpha n. Well, I will just define it to be equal to alpha n, actually. And this will give me the order of growth of all the other cumulants, and it is convenient to to take the constant equal to 1, if you want. Okay, so then I look at the third cumulant. So I also have assumptions to make on the third cumulant. So it's supposed to be a big O of alpha n. Okay, so let's say that it is equal to L times alpha n, and that L is convergent, so that should have something like that. Okay, and then I assume for the other ones that I just have this, but with a constant that is not too big. So I assume that kappa R of Sn divided by beta n is smaller, so I have to put a constant here times alpha n. And I want that this constant is, well, doesn't go bigger than r to the r for some c. Okay, so the list of these assumptions, this is the setting of, well, this is the method of cumulants for mod Gaussian convergence. And so what I want to show you is that if you have this, then you have mod Gaussian convergence for Sn, or well, for Sn renormalized. So if this is true, and then I will explain how to obtain this, then you have mod Gaussian convergence, and so you can control the tails, the moderate deviations of Sn. So then, if I look at, so Sn divided by alpha n to the 1/3 times beta n, this is mod Gaussian convergent. Okay, so why is that? Well, let's compute the generating series of Xn. So it's better to take the logarithm, because then it involves the cumulants of Sn. So this will be equal. So the first, so you don't have terms of order 1, because this is equal to 0. The first term, so it's equal to alpha n z squared over 2. And so since you normalize by alpha n to the 1/3, here you have to divide by alpha n to the 2/3. So in fact, you have this that appears here. Okay, so this is for the first term.
So is there an interpretation? What's the role of the TI here? I mean, everything else seems to be in terms of the S's. Is there assumption about the TIs, or
no assumption for the moment?
Just their
It can be
interpretation
anything.
in terms of the TIs. This is just about the S's.
For the moment, I just make assumptions on the cumulants, and then I will give a sufficient condition on the TI and on the structural dependency of the TI to get so that these assumptions are fulfilled.
It doesn't need to be a sum of something. I mean,
That's what I'm
Yeah,
asking.
actually, yeah, I'm sorry. So I've just
So
I've written it as a sum, but
at this point you're just
yeah,
giving theory about the S's.
yeah, exactly.
And later you'll give
exactly.
Sorry. Yeah, it was just to give an
I'm
intuition.
just trying to figure out how I should think about it.
It was just to give an intuition that the cumulants, they should behave in a multilinear way, so you should expect the cumulants to be of order, say, capital N to the R, but in some situations, in fact, they are much smaller. And so this is what these assumptions mean. And then, from there, you obtain a mod Gaussian convergence, and we'll give sufficient conditions when you have a sum of dependent.
So you'll tell us something later that
Yes.
says that if the TIs only are correlated with a few neighbors and non-correlated with
Yeah, or
everything
even with
something.
not only with a few neighbors, but with less than capital N neighbors. So not a complete graph, but something, even if you have something just sparse, it's sufficient. Okay, so let's continue. So here, so if I do the Taylor expansion of this series, so the first non-zero term, it corresponds to this second cumulant. So then you have the third cumulant. So it's L alpha n, let's say 1 plus smaller of 1. C3 over 6, but so again, I divide by alpha n to the 1/3 to the 3, so in fact, this disappears. Okay, and then I have all the other cumulants. So it gives me something like that. So I start at the fourth cumulant. Over 3 and sorry. Okay, so I claim that this quantity goes to 0. So why does it go to 0? Well, if the modulus is smaller than, so I use my assumption, it's smaller than the sum of this, and then you have alpha n power 1 minus r over 3, and so notice that this is a negative power of alpha n, and z to the r. Okay, and so here you have something that goes like r to the r, but here you also have a r factorial. So in fact, here you will have a convergent power series, and multiply by alpha n to the 1 minus r over 3, so this is at least alpha n power minus 1 over 3, so this goes to 0. Okay, because you can take in factor this alpha n to the 1 minus 4 over 3, because r is at least 4. Okay, so this doesn't count. And if you look at this, if you just take again the exponential of this quantity, what you get is mod Gaussian convergence with parameter alpha n to the 1/3, and for limit exponential of L z3 over 6. So Tn is alpha n to the 1/3, and psi of z is exponential L z3 over 6. Okay, so you have the same kind of mod Gaussian convergence as in the case of some of our IDs, but just from assumptions on the cumulants. And now what I need to do is to give you sufficient conditions on a sum of dependent random variables to get these assumptions on the cumulants. So just I don't want to forget anything. No, it's okay. Okay. So this is the third part. So this is the way to obtain bond on cumulants. So actually, so when you have a sequence of random variable Sn, so to compute the 3 first cumulants, well, this is just a computation that you have to do by hand for every example. So you just have to compute the asymptotics, but this is just in, well, mostly, so these cumulants, it's mostly the computation of the 3 first moments. So you just have to do that by hand. There is no recipe, general recipe, you just have to do it for each model. What is really difficult is to obtain this bound for the other cumulants, and this will ensure that this sum here doesn't count when you do the asymptotic analysis of the Laplace transform. So this is really what is difficult. This is really what we need this is really where we need the general result. This is not very difficult to deal with. Okay, so we want to have bound on cumulants. And this is, so the way that we are going to obtain this bound is related to the notion of dependency graph. So bound on cumulants and the notion of dependency graph. Okay, so what I do, so I'm going to consider, so this time really a sum of random variables. So S is a sum of random variables that are labeled by a set V. So in fact, so at the end, everything will depend on N. So here this set will depend on N, and the variables themselves will depend on N. but the bond that I'm going to use, it's really something that holds for every sum of random variables, so I don't need to, the parameter n is superfluous here, I'm just a statement on sums of random variables. Okay, so I suppose that I have something like that, and that I have a dependency graph. So what does it mean? So I suppose that V is a set of vertices of a graph. And so a graph, of course, it is given by a set of vertices and a set of edges. Okay, and I suppose that this graph is a dependency graph for my variables TV. So what does it mean? So it means the following. If I can split my graph in two parts that are not connected, then the corresponding subfamilies of this large family of random variables are independent. So let me write it. If V can be split into two parts with no edge between a point in V1 and a point in V2, then, so if I look at the subfamilies TV with V in V1 and TV with V in V2, these are independent families of random variables. They are independent. Okay, so it's better to look at an example just to be sure that we understand everything. So if I look at this graph, sorry. So if variables labeled by the integers between 1 and 5. So if this is a dependency graph, then it means, for instance, that T1, T2, okay, so I should put something like that. If I look at T1, T2, and T4, T5, there is no direct edge between something, so between 4 and 5 and 1 and 2, because you have to first go through the vertex 3. So these two families are independent. So you have to be careful that it's not just that they are not connected. So this condition here, it's not as strong as not being connected. It just means that you don't have a direct edge between the two parts of your graph. Okay, so you suppose that you have something like that, as you have a dependency graph, and what we need is a degree of the dependency graph. The degree is just the maximal number of neighbors of an element in your graph. So the degree of G is maximal number of neighbors of a vertex V in V, and I will also denote N, which is just the cardinality of the graph. So if it's a vertex set. Okay, so there is a bound on cumulants of S that only depends on N and D. And, well, okay, so you have to make assumptions on TV. So you suppose for instance, that this is true for every I and R. Then you can write a bound on the cumulants of S. So then the R cumulant of S, it is smaller in absolute value than, okay, so and N. It is smaller than that. So you have a bound on the cumulants that only depend on the number of elements and the degree of your graph. And in fact, this, so if you plug this, if you use this to compute such bounds, what you will see is that each time that you have a sum of dependent random variable, but with a degree d that is a small O of n, then you have mod Gaussian convergence. And also you have, well, so you have a central limit theorem, but even better, you have mod Gaussian convergence, and therefore the behavior of the tails that we have seen this morning. So with a limiting function psi, that is something like exponential LZ over LZ3 over 6. Okay, so this implies, and so I will give a more precise example in a moment. So it implies that if D is a small O of n, and so suppose also that you have this condition on, so that the Ti are not too big. For instance, you can suppose that the Ti are between 0 and 1 at each time, or well, between -1 and 1, for instance, to simplify. So if you have this, then there exists a scaling of S, so X, such that X converges in the mod Gaussian sense. So I can even give you the scaling in question. So you have to take X equal to S over D, D over N to the 1/3, and Tn then will be N over D to the 1/3. Okay, and the limit, so you have to compute L then, but the limit will be exponential LZ3 over 6. Okay, so yeah. Okay, there is something missing. So if you have this, and if the first cumulants converge, so by that I mean this in fact. So you still have to do this computation, but. So if you have both of these things satisfied, then you know that you have mod Gaussian convergence and you have everything that we have seen this morning. So what I'm going to do, okay, so first let me tell you about the proof. So this is actually quite difficult to prove. So it relies, so what you do is that, so since cumulants they are multilinear, you can expand this by multilinearity. And so we will get joint cumulants of the variables that appear on this graph. And so now you can use a dependency graph to, so it will tell you that some of these cumulants are equal to 0 because in your joint cumulant you have two families that are independent that correspond to two parts that are not connected in your graph. So it tells you that many sums, in fact, many joint cumulants, when you expand by multilinearity, are equal to 0. And so in particular, it tells you that you, so it gives you this coefficient, but then you have to compute, so the arguments that I've just given, it will tell you that this is of order big O of n with something that depends on d. And then you have to compute this function of d. And so this is quite hard, and it uses, so you have to rewrite the cumulant in terms of spanning trees of the dependency graph, so it is quite intricate, and I will not perform the proof here. We can try to show that at least it's a BO of n, but then to obtain this precise behavior, which is exactly what we want, because we want something to the r, well, we want something to the r, like that. This is quite difficult. So this I will just skip. And so I will give an application of this in the setting of random graphs. So this is a setting where we will really have...
This is where you explain 1/3?
This exponent
The
here?
convergence. The mod
Oh.
Gaussian convergence.
Oh yeah, so I mean, so okay, so the scaling is given by, so you look at this, and so the parameter of the Mod-Gaussian convergence will be given by Tn equal to this. So by that I mean, so of course, S now depends on n, D depends on n, and so on, and capital N and D depends on n also. Okay, and so the limit psi of z, which is what you lack here in this statement, so it's something like exponential something times z3, and the something it depends on the limit of the first cumulant that you have to compute by n for every example. So we'll give an example where we can compute actually everything.
And does D depend on the size of the...
Yes. So D depends on n and n depends on
But
n.
it's small compared to n.
Yes, exactly. You just want this to go to plus infinity. Okay, so let me give you a concrete example where you have this. So where you can actually do also a dependency graph that is interesting and obtain an interesting Mod-Gaussian convergence. So as an example, so we consider the following. So I take a random Erdős-Rényi graph. So what is this? So you fix n vertices. So let's say that I take n equal to 5. And for each pair of vertices, you, with probability p, you put an edge, and with probability 1 minus p, you do not draw an edge. So for instance, you can obtain something like this. Okay. Let's say something like that. So here, these 4 edge, I have my Bernoulli variable. So, and every edge is independent. So if you, when you choose your edge here, it is independent from the edge here, for instance, or from the edge here. Okay. So every ij gives at random an edge with probability p. And this independently for every pair ij, independently of the other pairs. Okay, so what you obtain is a random graph like that on n vertices and with a random number of edges. And what you are interested in is the number of triangles that you can find. So here there is no triangle, maybe I should add something. Okay, here there will be triangle in my random graph. So you look at the number Sn, well Tn, the number of triangles in your random graph. So by that I mean the number of families of 3 elements, I different from J different from K, such that Ij, Jk, and Ik are edges of my random graph. Okay, so in my example, if I count well, there are 2 triangles here, 3, 4, 5, and also, sorry, 2, 4, 5, and 3, 4, 5. These are 2 triangles. So here in this example, Tn is equal to 2. Okay, so this Tn, I can write it as a sum of binary random variable because I just look at every possible family of size 3, ij, jk, and then this gives me a binary random variable which is equal to 1 if there is this triangle and to 0 otherwise. So it's better to, okay, yeah, maybe here I should order them. And therefore, so this will be equal to 1/6 times the sum for every I different from J, different from K, of the indicatrix that I, J, K is a triangle. Okay, so I'm just a remark. So I'm working with triangle because you can, so everything can be written and the formulas are not too complicated. But in fact, you can look at every possible motif of a graph. So for instance, you can look at the number of squares or I don't know, pentagrams or whatever in a random graph G and P. And again, you will obtain Mod-Phi Convergence. It's only that the parameters are easier to write for this simple example of triangle. And this is already an interesting example. Okay, so the factor 1/6 is just because here we count on unordered sequences and here on ordered sequences. So this, the sum without the factor 1/6, I denote it Sn. And this is a sum of Bernoulli random variables. So I will try to draw a dependency graph for this Bernoulli random variables. Okay, so first, what is the cardinality of my set of random variables, where you have to count the number of sequences of size 3. So this is n times n minus 1 times n minus 2. You have n minus 1, n minus 2 choices for I different from j different from k. So n should be equal to this. Okay, so which is essentially n to the 3. Okay, so now what is the dependency graph? So if you have a triangle here, well, so I should, okay. Sorry. If I have I different from j different from k, so I do it in dashed lines. So, and okay, I look at another variable I prime, j prime, and k prime. Okay, and I look at the Bernoulli random variables that tells me if this triangle appears in my random graph, whether this appears or not. So these two random variables attached to the sequences I, j, k, and I prime, j prime, k prime, if they are not independent, then this means that you have some edge in common. So for instance, that this edge is equal to this one. Because otherwise, so for instance, if you have this situation, so let's say I, j, k, and this is equal to k prime, and then I prime, j prime, then these two triangles are independent. Okay, because they correspond to edges that are not the same. The edges are independent, and therefore the triangles are independent. So if your two sequences are just one point in common, then the corresponding triangles are independent. And of course, it's the same if they do not have any point in common. Of course, then the edges they will be disjunct, and they will be independent. So for these two things to be dependent, you have to have ijk inter I prime, j prime, k prime. So this should be at least of cardinality 2. Okay, it can, of course, it is if it is of cardinality 3. I mean, if the two sequences are the same, then of course they are not. They are also dependent. Okay, so this means that if your graph, you can take the following graph of dependency. So V is a set of sequences I, J, K. And it has cardinality, well, roughly n to the 3. And then for edges, you can take I, J, K connected to I prime, J prime, K prime, if the cardinality of the intersection is bigger than 2. Okay, but if you fix now ijk, the number of neighbors in this graph, it is bounded by a constant times n, because to choose a neighbor with this condition, so what you have to do, so first of all, you have to choose the two elements here that will be equal to 2 elements in this sequence. So here there are 3 choices. Here there are also 3 choices in order to choose 2 elements. And you can also, well, so for instance, pair ij with I prime, j prime, but you could also pair ij with j prime, I prime. So you have also a factor 2. And then for the remaining k prime, so let's say that ij is paired with I prime, j prime. For k prime, you cannot choose k, you cannot choose ij or k, so you only have n minus 3 possibilities. So the degree, it is bounded by this times n, for instance, or n minus 1. Yeah, n minus 1. Okay, so it's bounded by 18 times n minus 1, for instance. Okay, and this means that we have a sparse graph, because the degree divided by the number of terms is clearly going to 0. Okay, here you have n minus 1, and here you have n to the 3. So of course, d over n goes to 0. So therefore, you will have Mod-Phi convergence. So maybe I can just write the result. So if I look at Tn minus its mean, so what is the mean of Tn? Well, so it's a sum of each of these variable. It is a Bernoulli random variable of parameter p to the 3, because you have 3 random variables for each edge in your triangle. So it's Tn minus p to the 3 times the number of terms, and the number of terms, so it's n minus 1 and minus 2 divided by 6, so 3 among n. Okay, and so then you have to renormalize by n to the 5/3. And so there is a parameter here that depends on p, and which is related to the well, to the alpha n, to the limit of the second cumulant. So this converges in the Mod-Gaussian sense. With parameter n to the 2/3. And the limit that is explicit. So the limit, it is psi of z. So it's explicit, but a bit complicated. That's it. And therefore, so if you look at the fluctuations, so you can write the fluctuations of order So this times Tn, so of order n to the 7/3 of Tn, and you will have a result which involves a Gaussian tail and also this function. And so in particular, so here there is this factor 7 minus 8p. So according to the value of p with respect to 7/8, your tails will be either sub-Gaussian or much larger than a Gaussian according to the sign of this quantity, which is not something that you can guess if you look at, I mean, 7/8, there is no reason why this coefficient should appear on the random adversarial graphs and the number of triangles. But if you look at what our results tells, the tails of your distribution, they are not the same according to the sign of this quantity. Okay, so I should stop here because it's exactly the hour. So